and please go ahead.
Yeah, so thanks for inviting me to give this talk. So today I will talk about my PhD work mainly, which was on the energy loss and equilibration of highly energetic parton in QCD plasma. As you all know, this was done in Bielefeld with the Zuhn-Schlichten. I also had other collaborators, Yassin Metartani and Guy Moore and Nishus worked on this Guy Moore and Nishus we worked on this other project at the end of my PhD. So let me start by a kind of motivation for what we are looking for in this work, which is mainly so we want to understand the kinetic and chemical equilibration of high energetic partons in heavy ion collisions, and especially we want to include the possibility of these particles to be completely lost in the medium. And this is motivated also by this Phoenix collaboration, which will look at jets in RIC instead of the LHC, where the energy of the hard parton is maybe not so hard in the initial states, and so maybe they can be completely lost in the medium and thermalize with the medium. And since we know that the processes that equilibrate the QGP are strongly reminiscent of this jet energy quenching, so the same processes also are important for jet energy quenching. Maybe we can also learn about the QGP equilibration by looking at these strongly quenched jets. And lastly, just to point out that we try to develop an understanding of the dynamics and the semi-analytical insight. So we don't try to directly compare with experiments, and we try to find interesting dynamics that can be explored in Monte Carlo simulations or experiments instead. And so we know that the complete picture of jet evolution in heavy ion collision is a complex task that will require a solid understanding of the different stages, from the initial production due to the hard vertex to the vacuum shower. And then once the parton is resolved by the medium, then we have the in-medium fragmentation and energy loss. And then at the end, when it leaves the medium, we have the hadronization outside the medium. And so the full description will involve different processes at different scales. And that is why it is important to develop a robust theoretical understanding of each stage. And in our work, we will not try to develop this complete description of the in-medium jet evolution, but rather we focus on the particular aspect of the energy loss and equilibration of the parton once it's already resolved by the medium. And so we study this evolution using an effective kinetic description, which is based on the Boltzmann equation at leading order, where we consider the high energetic partons as this linearized fluctuation over a static background equilibrium. So then we write the distribution as the static background equilibrium plus the fluctuations, where we linearize the equations on this fluctuation. And then the results will be shown in this energy distribution, which is just taking the distribution with 3 powers of momentum to compute this energy distribution as a function of x, where x is this momentum fraction carried by each parton. We also keep track of exact conservation of energy, momentum, and valence charge, which will allow us to study the evolution from the high energy sector to the medium, including the thermalization of the hard partons. And at leading order, the process, there are two types of processes that needs to be taken into account. So we have the two elastic scatterings with number conservation, which are given in these three type diagrams. And then due to the multiples of scattering with the medium, these hard parton can then radiate in this medium-induced radiation, which can be written into an effective 1 to 2 collision rate. And we have here the three processes that are allowed.
Ismail, in the elastic scattering part, what is the gluon that you have there, and what are the quarks there? So one of them, I guess, should be the jet particle, but what about the other legs?
Yeah, that's the medium. So we have three quark flavors, and we have gluons and also antiquarks. And so the medium is equilibrated, and so depending on how we start this distribution, we either start it as a quark jet or a gluon jet, which just meaning one gluon going through the medium. Then it will interact with the medium particles in this elastic scatterings.
Maybe I try to ask in a different way. So on the right side with the RPM diagram, you have these tiny gluons, and
yeah,
and in those tiny gluons are somehow very soft ones, right?
Yeah.
The momentum exchange there is very soft.
Okay.
And the quark that you have there, that's something which has a big energy, which has an energy much bigger than the temperature scale, I guess.
Yeah.
So in this sense, on the elastic scattering diagram, what is what? Because this was never clear to me. That, so for example, P2, maybe it's a particle which has energy much bigger than the temperature scale, but is P1 the same? Or can that be a soft quark?
Yeah, because we linearize the over this fluctuation, so we don't have jet elastic scattering, because these also are subleading. So we always have, if this is a hard parton, then this will be the medium particles. Then we sum over all the possibilities. So here also, if this is a hard gluon, this will be medium gluon.
Okay. Okay, thank you.
But yeah, but I would maybe explain it more here when I'll talk about how we treat the treated the elastic scatterings in the first study. So,
okay.
So first we focused on the longitudinal energy loss. So by integrating out all the angles and the position of the distribution, we focus only on the distribution of energy. And we did this simplification for the elastic scatterings, so if you introduce a cutoff in the momentum exchange Q here between the particles, the elastic scatterings can be separated into small and large angle scatterings. The cutoff will be in the middle between the infrared cutoff and the UV. And since the large angle scatterings are parametrically equivalent to the small angle scatterings, in the first study, we keep only the small angle scatterings for now. And these small angle scatterings can further be simplified if you consider that this cutoff that the momentum exchange is small, then you can expand in the momentum exchange, and you can rewrite this collision integral into a differential equation, which is this Fokker-Planck equation with the source, with the current term and the source term, where the current gives you this diffusion and drag, and then the source term gives a conversion. The energy of the parton is not changed, but it can convert between quark and gluons. And then since we keep track of the exact energy conservation, so we have this diffusion and drag here acting on the jet, we also have the same processes but acting on the equilibrium distribution, which we call recoil processes. So these will so the energy lost from these hard parton will be deposited in the medium scales. And here the subtlety is that since we have this static background equilibrium, then this recoil will deposit energy in the soft scale, but in the fluctuation. And so this jet distribution will thermalize itself, and the background will always stay static and will not change. Maybe this answers your question. So now we can look at the energy loss, and since we have this exact energy conservation, then to talk about energy loss, we define a cutoff here to be 2 pi t, where we compute the energy stored in momentum larger than 2 pi t, and this we consider to be the hard particle momentums. And we look here at jets with energy 1,000 times temperatures, and we take the coupling to be 1. And here we have this high momentum particle energy as a function of the evolution time in this dimensionless time. And we look at 2 types of jets, either a gluon jet, where we start with the Gaussian in the gluon distribution, or a quark jet, where the energy starts in the quark distribution. So we have here the energy loss as a function of time. And so we see that the energy loss evolution can be separated into 3 regimes. We have the initial energy loss, which is mainly mediated by gluon radiation and recoil terms. And very soon afterwards, we have, when the intermediate regimes are populated, we have this energy cascade that sets in with the universality between the gluon and quark jet. And this is driven by radiative breakup via successive splittings, and it's very reminiscent of turbulence. And then at the end, we have equilibration and via exponential decay that can also be described with linear response. And now I will try to explain each stage of these regimes, starting from the early time behavior, where here we can study the evolution by considering a perturbative type, and by expanding the equation into a kind of perturbation, where, for example, here in the emissions. So here we consider a single emission, for example, for a gluon jet. So we have the initial jet, and then the gluon has a single emission either of a gluon or quark anti-quark pair. And we find that this distribution will follow the behavior of a single splitting in the intermediate range between the medium and the hard jet here. This is the momentum fraction, so the medium and the jet here sitting at 1 with the linear rising amplitudes. And so for the gluon, we have this 1 over square root x behavior, and for the singlet, which is the sum of quark and anti-quark, will be the square root x behavior. And this will lead to direct energy deposition into the soft sector which we can study by looking at the derivative of the energy stored in the heart momentum. So this plot I showed before, but the derivative in time. And so this will give us a flux of energy to the soft sector. And then the recoil also will lead to a flux of energy in the soft sector. But the recoil behavior will only be apparent in the medium scale, but not in this intermediate range.
Ismail, excuse me.
Yeah.
So when you say that the energy distribution is proportional 1/square root of x, that is typical for this BDMPS regime. Multiple source scattering induces emissions. What is not exactly clear to me is that in your formalism with this 1 to 2 emissions, do you actually include hard emissions in this? Is it possible to have single hard scattering induced emissions, like GLV type of stuff?
Yeah, sorry, I didn't explain this, but we use this AMI rate, which is resoundant, so it includes both the LPM suppressed part and also the opacity, this TLV type the rate is also included in the soft regime. Is recovered.
And still, when you do the early time expansion of the differential equation, you only sensitive to the BDMPS emissions, you said?
Yeah. Because because when you, so the soft emissions will lead to mostly things that are, I mean, in the soft scales, in the medium scales, but in the intermediate scales, you are mostly sensitive to the BDMPS. So here we consider the BDMPS a kernel that leads to this 1/square root, as you said.
So this comes from the fact that in the first line and then the first equation in this page, the K's that you have there are the BDMPS one or some.
Yeah, because for the BDMPS there's this parameter of Q hat, right? That is kind of free. So we match the Q hat to AMI. So yeah, so we use the BDMPS kernel, because it's known analytically, and then we match the Q hat to AMI because the AMI is what is actually used in the simulation, and so we match the coefficient, I guess, to AMI, and then the behavior is the same.
Okay, thank you.
Yeah, so we can look at the distribution at early times. So here we have the gluon distribution times square root x. And on the right, we have the singlet times square root x, which is again the quark plus anti-quark. And this is for an initial gluon jet. And we compare it with the rate. So on the left for the gluon distribution, we look at the rate of gluon splitting, and we see that here in this gray dashed line, which is the single emission spectrum, we can recover the distribution at early times very well. And we have the recoil here that we can also describe analytically. And on the right for the singlet, we have again the single emission spectrum recovered, and the recoil here for the singlet actually has a negative behavior. It's this that I plot in these dashed lines. And this can be understood as just some particles from the medium that are kicked into higher momentum. And since the medium distribution does not change, then this distribution becomes negative. However, soon afterward, you can see that the single emission the distribution starts to deviate from the single emission spectrum, especially in the singlet distribution. For the gluon, coincidentally, the behavior stays the same. And so this is when you have this energy cascade that sets in, which can be understood in an analogous way to a turbulent cascade, for example, from hydrodynamics, where you have these vortices that are divided into smaller and smaller vortices. Here we have the hard parton that splits into lower energy partons, and so we have this hard energy injected from this hard parton that travels through the cascade all the way to the thermal bath, following this inverse energy cascade. And here again, we can describe the intermediate, the behavior in the intermediate momentum range. And this is given by the stationary turbulent solutions, which are associated with the scale invariant energy flux. So if we compute now this energy flux, but up to an arbitrary scale lambda instead of 2 pi t, you find that this scale dependence actually drops out, especially when you take a small scale. And using this as a constraint, you can find the behavior of the distribution, which is this stationary behavior. And coincidentally, it's 1 over square root x for the gluon and singlet distribution. So and if you remember from the early time behavior, the gluon was again going as 1 over square root x, so it doesn't need to change behavior, while the singlet needs to go from square root x to 1 over square root x. And this comes with in the scale, in the energy flux, we have this time-dependent amplitude, which will account for the injection of the energy due to the radiation of the hard particles. And we can also study the chemistry by looking at the ratio of the singlet to the gluon distribution, and we find that this is also fixed by the splitting from gluon radiating quark divided by quark radiating a gluon, which is fixed with this stationary turbulent solution. And so if we use now this estimate of the soft radiation and recoil the deposit energy directly to the medium scales, and then we have this linear behavior coming from the energy cascade, we can look at the energy loss rate, which is just again the derivative of the earlier graph. Here we divide by the Casimir to match the early time behavior between the gluon and quark jet, and we see that we can describe very well the evolution using these two estimates. And we can also look at the turbulent behavior by looking at the distribution directly. Again, for here initial gluon jet, we see this stationary behavior here. Since we plot the square root x times the distribution, we have this flat distribution here in the intermediate range, which is this turbulent behavior, and we see this for both the gluon and the singlet energy distribution. Now, in the late times, ultimately the jet will equilibrate with the medium, and we can study this if we write the equation of motions as an eigenvalue problem, since we have a linear equation. And we find the zero modes which stem from conserved quantities. So here we have energy and valence charge conservation. And their eigenvectors are the asymptotic behavior that this distribution will end up with, which will be just a small perturbation over the equilibrium, since we have this equilibrium plus a linearized perturbation. And then the low line, and this we recover here at very late times. Here in green, we recover this equilibrium, which is we know analytically here in black dashed line. And then the low line eigenvalues will describe the equilibration at late times. So here, if we look again at the energy loss rate, but now for different jet energies, we can describe the very late exponential decay by using the first eigenvalue. However, we see that especially for hard partons, the initial and so hard initial energies, we see that this exponential decay happens at very late times where the parton has lost nearly all its energy. And so this near equilibrium physics cannot be proved by these hard partons since they're genuine non-equilibrium probes. On the other hand, maybe these lower energy partons can be used to study this near equilibrium physics more than the very hard partons.
Excuse me, Ismail, can you go back to the eigenvalue?
Yeah.
What do you mean here by this index I? Just a
the eigenvalue.
Yeah, but you say that there are zero mode and first. What do you mean by lambda I?
I mean, we sort them in the absolute value. So all the eigenvalues are negative, and then we just sort them by this. The zero mode is the first one, and then the smallest eigenvalue is is lambda 1. But then yeah, we still didn't work on higher eigenvalues.
Maybe it's a more fundamental question is, how do you end up in this eigenvalue problem? I almost understand the left side of the equation. I don't exactly understand the index I, but how do you end up in the eigenvalue problem here?
Because it's just because it's a linear equation, then you can turn it into an eigenvalue problem because it's a linear equation. And then since the way we do the numerical evaluation of the simulation, we actually use matrices. So computing the eigenvalues was just a given for us. But I mean,
but what is I?
Because
is it the xi or tau I? Because it looks like di, it's quark or gluon, or singlet or gluon.
Yeah, I mean, this you can do for each. I mean, you can think of each particle as just being in the vector. So you can call di as a kind of a vector where you have the gluon and the quarks.
Yes.
And then you can think of the collision operator as kind of a matrix, so a linear operator that operates on di on d. So di, I just call it di.
So
yeah, you're right.
I
think maybe I understand the yeah, so di will be each eigenvector. This is what I mean. And the lambda I will be the eigenvalue of that eigenvector.
Yeah, so it's lambda ij dj, and then you diagonalize it. I see. Okay.
Yeah, yeah, exactly. So yeah, maybe it's Cij dj, and then it can be equal to lambda I di.
Okay.
Since you diagonalize.
And can I ask on the next slide, when you have this equilibrium part, so equilibrium meaning it has no time dependence anymore. So I don't, so the how you start, that you say that you have the equilibrium distribution plus this perturbation that you linearize in. And then you say that in the perturbation, you don't, the perturbation can only interact with the background. So how this, so how this equilibrium even arises in that case?
Because we have energy conservation, and so this this fluctuation has some energy. So the equilibrium has an energy and it doesn't change, right? Because it's static, and this fluctuation also has some energy that will thermalize, right? The hard partons will lose their energy, and so this energy at the end will end up being deposited in the medium, and the way it is deposited is it just the medium distribution gets changed by a small perturbation. And so, for example, here in the singlet channel, the medium has a small delta T, so the temperature somehow changes by a small value, and this is the fluctuation on top of the static background. But
so
yeah,
in the previous slides, when you calculated how much energy is deposited below P times the temperature, you feed that as a source term to your background. Do I?
Yeah, but we don't need to do the source term, because the Boltzmann evolution just gives this, right? Because I mean, we just solve this equation, and so this just leads to a stationary distribution where, so this D is the fluctuation, right? Mm-hmm. It doesn't include the equilibrium distribution. And so these, yeah, and especially these elastic terms just give you this equilibration of the soft sector.
So there's dotted lines. So the full equilibrium distribution would now be n Boltzmann plus the dotted line.
Yeah, exactly. Yeah. Yeah, because here we plot only the fluctuation, so the full equilibrium is the n Boltzmann plus the dotted line, which should be just a small fluctuation on top of the Boltzmann equation, the Boltzmann distribution.
So the delta T, is that a universal number, or it depends on the energy, or?
This delta T depends on the hard parton energy.
Yeah. Do you know how, or do you have any?
I mean, it just comes from energy conservation. So we usually start with we usually, what they call it, normalize the distribution that the energy is 1, that the energy is E, right? Some number times the temperature, and then delta T, I don't remember exactly what is equal, but I think it's on the paper. Mm-hmm. You can just do some compute it. Because the distribution is just a temperature derivative of the equilibrium distribution, because you have this like Taylor expansion, and so the first order is just the temperature derivative, and so when you do this temperature derivative, you can compute the energy and then normalize it so that it gives you the same energy as the first hard parton, and then you can find delta T.
Yeah.
And
how does it scale with energy? You have any idea? I mean, it's like
I don't remember. Sorry.
No problem. I'll check your paper.
Yeah, because I usually normalize this derivative. I mean, this equilibrium distribution, I usually normalize. And so for me, I usually delta T, I take it to be 1. Every time the normalization is what I don't remember. I mean,
okay.
Yeah, and so on here I don't show this, but for the valence channel, then because there you have valence conservation, and then there you have actually delta mu, and the distribution will be derivative over the chemical potential. And now, lastly, we can also look at the chemistry by looking at the ratio of the quark to gluon distributions. So here, meaning when it's above 1, then you have more quarks, and then when it's lower than 1, then you have more gluons than quarks. And so we look at the quark jet here with the full lines and the gluon jet with dashed lines. And on the left, we have early times to intermediate times. And so here we can see separation of you can see how the chemistry depends on the momentum fraction. So here at large momentum fraction, we have the jet core. So here we have quark for quark jet and gluon. And then in the intermediate times, we go to this Kolmogorov spectrum at the intermediate range, which is comes from this turbulent spectrum, this stationary turbulent solutions. And then in the soft sector, we go closer to the equilibrium chemistry. And then at late times, what we find is that once the jet starts to lose most of energy, then we find that hard partons are most likely to be quarks. Even for a gluon jet here with dashed lines, we have more quarks than gluons in the hard particle, which makes sense since the gluons lose their energy much faster than the quarks. But this is something interesting to look at, and we conclude that the strongly quenched jets should be quark rich. Now, beyond this longitudinal energy loss, we also looked at the angular cascade by looking at the energy loss out of cone. And so now we consider an angle-dependent distribution where theta here is the polar angle around the initial hard parton that goes in the z direction. Then you have the polar angle from 0 to pi, and we integrate out the azimuthal angle. And since we want to look at how the energy goes out of cone, then we consider not only the small angle approximation, but now we replace these 2-to-2 scatterings with the full matrix elements that I showed first, these 3 type diagrams, where we use HTL propagators to deal with the divergences. And on the other hand, this effective 1-to-2 scatterings, we keep the same using, again, the AME rates in infinite media. Now we can look at the energy loss and thermalization by looking at the energy distribution here, where I sum over all the quarks and gluon. This is now for a gluon jet with 100 times temperature, and we take the coupling to be 2 here. And so the distribution here is a function of momentum fraction, where here we have 1 where the jet sits, and then we have the angle here that goes from 0 to pi. So the jet sits here in gluon starts here in the z-axis, and we see that in the early times we have this energy cascade, this collinear energy cascades that transfers this energy from the hard parton to the soft scale, but since it's collinear, it stays in the small angle region. But then right afterwards, this 2-2 scattering leads to the broadening of this energy that is deposited in the soft scale sector. But we see very negligible broadening of the hard particles. And then in the late times, this energy is fully broadened to very large angles. And what we see mainly is that the energy loss out of cone is mainly due to this energy deposited in the soft sector and not due to the hard particles broadening to large angles. And we can corroborate this further by looking at the energy evolution. And now, so now we can look at how the energy is lost out of cone by integrating out the distribution in momentum fraction and in angle, but by doing a cutting angle to see how the energy goes out of this cone R. Or we can look at only the hard particles by integrating out the momentum fraction up to 2 pi t again, and again looking at the same constants. And so here we have different cone sizes from 0.62 to 0.11, and we have in this full lines the full energy without separating the soft sector, and then in dashed lines we have this soft sector, only the hard particles without the soft sector, and then these areas shows the difference. And so if we look at the small cone sizes first, we see that the soft sector does not play a major role, and so the energy evolution and also the energy stored in cones is mainly the same. We see similar energy loss in both momentum regions, while for larger cone sizes, this soft sector not only carries a substantial fraction of the equilibrated energy here at late times, the early time energy loss also diverges and has different behavior. And this is explained by how the energy is lost out of cone. So, which is mainly due to this broadening with the elastic scattering. So we also used our evolution as a toy model to compute what is known as quenching factors, which can be related to the RIA. Yeah, and we looked at the kind of leading parton quenching here for a quark and gluon jet at different times, and as a function of PT, and we see that which was computed as a convolution with our evolution, and we see kind of we recover the qualitative behavior of RRA, mainly that the soft particles are more suppressed than hard partons, and how the gluons here in full lines are much more suppressed than the quarks in dashed lines. And on the other hand, we also try to look at what we call jet quenching factor by looking at not the full energy, but only the energy in some cone size inside the cone, and by changing the cone size here from small 0.11 to 0.62. And we again did the separation between the hard particles by looking at the energy stored in hard particles only, and by looking at the full momentum range. So the full momentum range is the dashed lines, which are less suppressed than this full lines, which account only for the hard particles. And then this area here shows us again the sensitivity to the soft fragments. So when we go to small angles, we see that the soft fragments do not play a major role in the energy, while when we go to larger and larger angles, then this soft fragment thermalization is important. And so if we compare these two, what we see is that the hadron quenching, which depends mostly on the hard constituents, depends mainly on this turbulent energy cascade, which is driven by this in medium splittings, and so it can be used to probe this in medium splitting collinear branchings, while the jet quenching recovers energy from the soft sector for large cone sizes. So then it can be used to understand maybe medium response and how these soft particles thermalize with the medium. Yeah, and we didn't compare with experiments, since here these results we have the energy loss is currently overestimated due to neglecting this finite size effect, since we use the ME rate so for the medium induced rate emissions rates, and this is work in progress to include finite size effects. Now we have seen.
Excuse me for this. So
yeah,
did you include any kind of vacuum emissions in this study?
No.
Because then
no,
maybe it's a bit an overstate to call these jets then.
Yes, of course. Yeah, this is what we do is not really jets. We look at this resolved partons in the medium. So you are right that this, yeah, but with this jet quenching factor, we just try to capture how the energy is lost out of cone. So how.
You know, we have some work on these quenching factors. And in that case, you can, for example, simplify or assume the problem that you have, you know, this initial, like this, sorry, let me tell again. So, you know, for example, the work by Paul Coco. So he has this time factorization. And if you just want to estimate like how important are vacuum emissions, then you can calculate in the first stages how the initial distribution, this dx, changes because of vacuum emissions. And you can source, for example, those in your those particles or those distribution with your framework to give to get a wild guess like how would change your result.
Yeah, this is what we were thinking of doing next. But yeah, because now we still use this infinite medium rate, so I think even if we include this vacuum radiation, we still will overestimate the suppression, and so yeah. So next we will be working on finite size effects, and I think then it will be interesting to look at these fluctuations of the vacuum emissions.
Also, your previous study misses finite size effects, right?
Yeah. Yeah, so this last part will be about a different thing, but yeah, so we have seen now so far that this in medium splittings are the dominant effect of energy loss for this hard parton in the medium, and so to understand the energy loss, it is important to also understand this in medium splittings. And on this last project, we try to include non-perturbative effects in medium splittings. So far, there are several approaches available for computing this medium-induced splitting. So the AMI is what you use, but there are other approaches like the MPS, what you said, or GLV, and so on. That all give this effective medium splitting. And all the different methods require a description of the interactions with the medium, which gives this multiple soft scatterings with the medium. And usually this is given by the elastic broadening kernel. And these approaches usually use perturbative calculations to find this elastic broadening kernel, and the ones that are usually used in the literature are perturbative calculation as well as description of the medium particles. So if you describe the medium particles as static screen color centers, then you can find this Yukawa type potential, or in the HTL approximation, you can describe the medium as a dynamical moving charges, and then you get this resummed HTL potential. Or if you approximate, if you go to the hard parton limit, where then the particle experiences this multiple soft scatterings with the medium, then you can write it as a kind of broadening potential in position space that leads to the fact that you can solve this in medium splittings analytically and obtain this harmonic oscillator type potential. And so all these approaches either rely on approximation. Yeah.
Like, can I ask something very silly? Like, is this collisional kernel related to the 2-to-2 processes also that you have?
Yeah, it is the 2-to-2 process. I mean, you can derive this one. You can derive from the matrix element if you just plug the HDL propagators and you take you take the parton to be hard, and using some approximations, you can actually derive this from the 2-to-2.
So it's the elastic scattering of a hard parton on a nearly thermal medium.
Yeah, on a thermal medium, not nearly thermal. And you consider the parton to be with such high energies that it doesn't lose much. So you can neglect how much energy it loses, but it only gains like momentum transfers to its direction. And this transverse momentum is this Q here, because Q here is a 2-dimensional vector, it's not 3-dimensional. So you integrate out the direction, the longitudinal direction of the parton, and you consider that it only receives kicks that kick it in the transverse direction. And this gives you this potential. Yeah. Yeah, so these potentials I showed are either approximations or potential obtained from perturbative calculations. However, what we know is that due to the infrared problems at high temperatures, the perturbative expansher encounters what is known as an infrared wall when additional gluon loops are not suppressed with the coupling, and so each since each loop gives rise to a factor of T over the gluon energy squared, and for soft gluons, this gives rise to 1 over G squared T. And so this breaks down the perturbative expansion. And one way to solve this problem is to use effective field theories of QCD at high temperatures coupled with the lattice calculations. One such theory makes what is known as electrostatic QCD, which makes use of the hierarchy of scales between the soft scale GT and the hard scale pi t from the first Matsubara frequency. And since for large temperature larger than the critical temperature, we expect the coupling to be small, then we have this large separation between GT and pi t. And so by integrating out the hard modes larger than GT, which leaves only the gluon zero mode, and this gluon zero mode decouples from a four dimensions to a three-dimensional field coupled to a scalar field, which is this A0. We end up with this 3D effective field theory known as electrostatic QCD. And so for temperatures well above the critical temperature, one can use this electrostatic QCD to compute the elastic broadening kernel. And perturbative calculations were done to obtain the leading order and next to leading order broadening kernel, but here the order is in EQCD perturbative calculations. And so in here I show from this paper of Cowell the next to leading order and leading order kernels, and times the Q perp to the 3 as a function of this Q perp momentum exchange. And what we see is that even at a small coupling, we see that for small enough momentum exchange, the next to leading order has a much different behavior. Actually, it goes as 1 over Q to the 3, while the leading order goes as 1 over Q squared. And so we have this large difference between the leading order next to leading order. And this hints at the breakdown of this perturbative expansion in EQCD. And so non-perturbative contributions has to be calculated. And these can be extracted from lattice calculations by putting this EQCD on the lattice. This was first done in 2014. And then in 2020, Gaimura and Nishosa were able to do the continuum extrapolation, and they found the broadening kernel, the continuum extrapolated broadening kernel in EQCD. However, the result shown here in this paper is for the broadening kernel, EQCD broadening kernel, which is not exactly what the EQCD broadening kernel we're looking for. Since EQCD is an infrared theory of QCD, they should both match in the infrared, but they can be different in the ultraviolet. And so we need to do a matching to QCD. Firstly, here I show just how we get this broadening kernel in impact parameter space as this zero subtracted Fourier transform. And so, yeah, and here we do the matching by subtracting the wrong ultraviolet EQCD behavior and supplying the right QCD behavior, which is computed from the perturbative calculation. This is just a side note, but this is the same way this next to leading order is also obtained by doing the matching to obtain the full QCD curve. And so So we take two temperatures from the lattice calculations, so 500 MeV and 250 MeV. And we do this matching and we obtain these data points here in orange for 250 and in dark blue for 500 MeV. So here we have the broadening kernel as a function of impact parameter. And what we find, first of all, is that if we do this, we show the broadening kernel as a function of impact parameter by taking the impact parameters in units of 1/GT. We find that the coupling and temperature scales out, and the broadening kernel for 500 and 250 MeV scale on top of each other and have similar behavior. Before I talk about the other plots, I show here the asymptotic behavior of the broadening kernel. So the long distance behavior, so for large impact parameters, it was shown that the kernel, the QCD kernel, should follow an area law behavior with some subleading logarithmic correction. So the main behavior is this area law, which is its constant plus a linear term that comes with this sigma QCD, which is the string tension that we compute by fitting to the data. And then the subleading log is just useful for the spline for the numerics.
Excuse me, Ismail. When you show the lattice calculation, and you also show that the long distance behavior, no, you show the short distance behavior on that plot, and the next to leading order. So
yeah,
so there is deviation at short distances, and there are deviations at long distances. So in both sides. And could you comment on why is that? Is it because there is a finite size of the plasma in the lattice, or?
Deviation from what to me?
So on the left plot.
You mean the errors here?
Mm-hmm. And it doesn't match the red dashed line.
Yeah, let me first just finish this short distance behavior and then come back to your question.
Okay.
Because this maybe will explain. So in the short distance, we do this. So the short distance translates to the UV. To the UV in momentum space. And so the kernel should follow the same behavior as the leading order, because that's where we do the matching to QCD. And so it is matched to the leading order. And and this is given by this b squared log b behavior plus this q hat 0, which is which sets the scale where we do this logarithm. And so this is to answer your question. So here the red dashed lines is this a short distance behavior that we match to. And so this deviation here is because we trust in these places. Actually, it's not that large of a deviation since we have a logarithmic scale, but here we trust that the behavior should be like the leading order, because this is the UV where EQCD should not be used, since it's the infrared effective theory of QCD. So I think this answers your question for the deviation here. And then for the long distance, we have this larger error bars, and we try to match this area law behavior by fitting string tension into this last data points, and we obtained these two plots for 500 MeV and 250, the top one. And so this, and then we match the kernel, the spline that we construct into these long distance behavior. So the deviation is just because we couldn't match exactly a line that goes through these points and also fix the string tension that we fit. Maybe this answers your question.
So is this electrostatic QCD contains the ultraviolet part of QCD?
No, it doesn't contain the ultraviolet. It's just an infrared effective theory.
Okay.
But these data points are already should contain the UV because these points are already the match broadening kernel. It's not just QCD.
Mm-hmm. Okay.
But yeah, but here we just try to keep this because we construct a spline that needs to go through these data points and as well as these behaviors at the extremas. And so we try to make it as smooth as possible for numerical stability. Because if we try to go through each point, then it will become kind of not so smooth. But we have a small band here, which I don't know if you can see it, but this band is due to where we do the switch between the extremal behavior and the data points. And now we can compare with the earlier calculations, which give us this leading order and next to leading order EQCD kernels, which are matched to QCD but obtained from EQCD perturbation. And so we have here the leading order in orange, which has this, which recovers the same behavior at short distances, but it has very different behavior large distances. However, the next to leading order, which also recovers the infrared, but at later scales, and at long distances, also has this linear behavior, but with a very different string tension. This is, we think, is coincidental that they have the same behavior. Yeah, but here the string tension is much different than what we get from the lattice results. Now, using this, we first computed the medium-induced splitting rates in infinite medium using this AMI approach, and where we just changed the broadening kernel between the leading order, next to leading order, and then the two different temperatures. And here I show the splitting rate of a quark radiating a gluon, where the quark either starts with 10 times the temperature or 100 times the temperature as a function of the gluon's momentum fraction. We first see no remarkable difference between 250 and 500 MeV, since we scale out here g to the 4t. And so this was expected since the broadening kernels also display this nice scaling. We see that we recover the LPM suppression at large momentum. So this is what you asked before. We recover this with the MPS type as a large typical momentum, and we recover the beta Heikler non-suppressed rate, but here is at very small momentum fraction. On the other hand, when we compare the lattice results with the perturbative results, we see that at large typical momentum, where we have this LPM suppression, the lattice result is closer to the leading order. And this makes sense because this probes very short distances where the matching is not QCD. And on the other hand, at small typical momentum, we see that the non-perturbative results has a similar behavior to the next leading order, since they come both with similar behavior, but we have a difference here due to the difference in the string tension. Now, next, we wanted to compute this medium-induced splitting rates, but in finite medium, and this is usually done in momentum space, since it simplifies. And so we had to transform the rate back to momentum space. And this is what we obtain here, the 500 MeV in purple and 250 in blue. Here you can see the bands that are larger. So this is the same band, but was very small in the short distances becomes here larger when we do the Fourier transform. Again, here we have the infrared behavior, this string tension behavior that becomes 1 over Q to the 3 behavior, like the next to leading order, but they come with a different prefactor due to string tension. And here the leading order goes as 1 over Q squared. And then in the UV, all the different rates go to the same behavior, which is this hard tail of 1 over Q to the 4. And following this approach of Kawau and Gale, we compute now the medium-induced splitting as a function of the evolution time, or can be seen as the time of the hard partons spent inside the medium, where we have here again quark radiating the gluon, where the quark's energy is 300 times the temperature and the gluon's momentum fracture is half the quark's energy. We see here the splitting rate again computed using different approaches, and on the bottom is the ratio to the leading order result. So again, the 250 and 500 MeV results keep a very similar results, except here we have a slight shift because I show here the evolution time in physical scales. What's interesting is we see that this lattice result actually starts lower than the leading order before it saturates between the leading order and next to leading order that we saw in the AMI approach. And when we look at the ratio, we see that actually the non-perturbative results stays within a band of around 50% of the leading order, while the next to leading order can become as large as twice the leading order. So we had this next to leading order overestimates the splitting rate. And yeah, maybe I go to the conclusion. So as a summary, so the main topic of my work was the evolution and equilibration of highly energetic partons in the static thermal QCD, where we studied the dynamics using a linearized kinetic theory, QCD, at leading order, and we made sure that we include the soft sector dynamics by keeping the Bose enhancements and Fermi separation, which allowed us to follow the energy from the hard parton all the way to the medium scales with the back reaction onto the medium. What we saw is that the energy loss is governed by the inverse energy cascade, which is driven by successive splittings. We also saw that the mechanism underlying energy loss can be similar to QGP's thermalization, especially for these low energetic partons, which are more sensitive to the medium scale. Well, on the other hand, when we looked at the out of Kohn energy loss, we see that the high energy distribution stays collinear, and the energy at large angle is mainly sensitive to the soft sector, to the energy deposited in the soft sector. And so while the hadron quenching is maybe more sensitive to this in medium cascade, collinear cascade, the jet quenching is more sensitive to soft physics and can maybe be used to study this thermalization with the medium. In the end, we had this project where we used this novel broadening kernel, which incorporate these non-perturbative contributions computer using this dimensionally reduced theory of QCD on a lattice. We computed then the medium-induced splitting radiation in both infinite and finite size medium length. We saw a sizable difference with results using perturbative rates that are usually employed in the literature. And so this maybe hints at interest in physics to investigate. And so as outlook, naturally, we can extend this leading order treatment to next to leading order, meaning this effective kinetic description. And this can easily be done when we do the separation between the soft and the small and large angle scatterings. And we can also try to explore this non-perturbative contributions into the effect, into the kinetic evolution. And, in order to compare with experiments, one needs to extend the framework, like what Adam was talking about, by including more realistic models, which includes vacuum-like emissions and finite size effects. And also this background here was always static, and maybe by including a more dynamical background will be important. And so this jet thermalization we think is important, as I said, because of this S-Phoenix collaboration, which will focus on jets at RIC instead of the LHC. Yeah, thank you for this.
Okay, great. Thank you very much, Ismail. It was a very nice talk, or very nice topics. It's a bit, we run out of time a little bit,
Sorry.
But it's fine. Are there any questions from the audience?
I have a question related to this, to your conclusion about high energy versus low energy jets, right? And it's also related to this kind of intermediate behavior and late time behavior. So, like you said that the late time behavior is achieved more quickly now. Well, more quickly. You rescale by the energy, right? So the late time behavior is more seen in the low PT jets, right? Low energy jets, low energy partons.
Yeah. Yes.
And in this late time behavior, you had this analysis of eigenmodes, and you found the delta T. I mean, how much energy is dumped into the medium, how much hotter is the medium, right? So,
yeah.
Locally, but you mentioned that the high energy jets, they are kind of partons. They are you only get to this kind of regime at times when you already lost so much of your initial parton that you cannot really distinguish a jet anymore. There's no more. There's no more jet kind of. So it's just it would. Yeah. So but what about like a finite energy, like a finite length analysis? I mean, so let's say the jet went through length L, and can you then say how much energy was deposited in total? Like, yeah, it's this dE over d tau, right? So the energy goes below the 2 pi t, for instance, something like that.
Yeah, I mean, if you think, okay, we will forget that we are using an infinite medium rate, and we we say, okay,
Yes.
after some time, we can just say, okay, the jet has left the medium after, let's say, some time here. And then you say, okay, this is the energy that was deposited, right? This is what you mean.
Okay.
You stop the evolution here and say, okay, this is how much energy was deposited. But
yeah,
but
that's true.
the question of studying near equilibrium physics.
But it hasn't yet thermalized, right? So it's not as easy to interpret it as just delta T somehow, right? It's still, or how is this?
I mean, it does thermalize quite fast, but the question is, because this energy, because when you look at these hard jets, the main mechanism of this energy loss is the emission. And so in this turbulent cascade, so this energy went all the way from this large scale to the soft scale. And so you don't have this near equilibrium evolution. You have a non-equilibrium evolution which follows this turbulent cascade. But if you look at this soft jet, then you can think of it as just a small perturbation on top of your equilibrium, and then you can study it with the near equilibrium evolution. So our thinking is this is closer to what how the QGP will thermalize than a very hard jet that loses its energy. It sends it to the soft sector, which maybe has some mechanism that the QGP does, thermalization doesn't go through, because it's in kind of very far from equilibrium.
So you mean that this intermediate stage is much shorter for low energy jets? They go more quickly to this kind of behavior, where the radiation and the scattering are of the same order. So you basically neglect the radiation there, or
I mean, you don't neglect the radiation. You just you just can use near equilibrium methods to study it.
Okay, great. Is there any question?
I have a question. I'm still a bit confused about the concept of equilibration in for the parton or the jet. You show a plot at the late time. The ratio is saturized somewhere, right? At in early plot, maybe 12 or page 12 or earlier. Maybe. You just Is this plot show?
You mean the energy saturizes?
So does it mean no matter how long we evolve the jets, there will be some energies above 2 pi t in the medium?
Yeah, this is because, I mean, 2 pi t was not the best scale we could choose, because the equilibrium distribution, when you look at the energy distribution, the distribution keeps going to the right, and if you look at 2 pi t here, you still have some particles that are larger than 2 pi t. But this is just the definition of the equilibrium distributions. And so, yes, but the distribution doesn't change itself. We just, if we went to maybe 3 pi t, it would have been maybe better. You can see that the energy goes to almost zero, but this is just an arbitrary scale that we chose as the soft scale. But yeah.
So
if you look at,
so physically, why this part of energy couldn't be into the medium finally, or because of some
they're part of the medium. I mean,
they're part of the medium. But the medium was hotter.
Yeah, this is
delta T.
Yeah, exactly. So the medium is hotter, so it gets pushed a little bit to the right because it's hotter. And if actually, I didn't talk about the thermalization in this out of cone, but here you can see that you have some negative here because here we have momentum conservation. So the medium doesn't only get hotter, but it gets a little bit boosted in the Z direction because the parton was going the Z direction. So some particles are eaten out of the other side of the jet and they're put into the direction of the jet. So this also is the same, but here just the medium gets pushed. So it gets a little bit more momentum than.
Okay, thanks.
But I think if you look at the Bose distribution itself also, and you look at the energy distribution, it also has some particles that are a little bit larger because when you do this, you multiply by momentum and then you push the distribution a little bit to the right. So you have very small amount of particles, but they have a lot of energy, so they contribute more than the ones that are soft, even though you have more soft particles there.